Solve the system x prime equals a times x, where a is equal to this 3 by 3 matrix, where the first row is 5, negative 4, 0. The second row is 1, 0, 2, and the third row is 0, 2, 5. So here we're going to find the eigenvalues by solving the determinant equation. Determinant of a minus lambda I is equal to 0, where a minus lambda I is subtracting lambda across the diagonal. So it's going to give me 5 minus lambda, and then negative 4 is 0, second row 1, and then 0 minus lambda is just negative lambda, 2, and then 0, 2, and 5 minus lambda. So I'm going to find the determinant by expanding across the first column. So that'll give me 5 minus lambda, and then if I cover up the first column and the first row, it's going to leave me with this lower right 2 by 2 matrix, which has a determinant of negative lambda times 5 minus lambda minus 2 times 2, minus 4. And then I get minus 1 times the determinant that remains after covering up. Let me cross that out to make it easier to see. After crossing out the second row and first column, so that leaves me with negative 4 times 5 minus lambda minus 0, and then plus 0 times the matrix that I would have up in the upper right. But 0 times anything is 0. So because I know I'm going to get a lambda to the third, I'm going to see if I can factor. And I see 5 minus lambda, 5 minus lambda, 5 minus lambda. So I'm going to, I guess maybe I should have kept that out. I'm going to factor out this 5 minus lambda from my first term. And from my second term, after you take away that minus 0, then this is just a product. So I'm going to factor out the 5 minus lambda. And then I'm going to expand here to get lambda squared minus 5 lambda, and then minus 4. And then here, minus 1 times minus 4 gives me a plus 4. So notice that the minus 4 and the plus 4 cancel. And I'm going to be able to factor out a lambda. So factoring out lambda gives me a lambda minus 5. And lambda minus 5 and 5 minus lambda are opposites. So they can be combined, but it's going to give me a sign, a negative in front. So I have negative lambda times lambda minus 5 squared equals 0. So this is going to give me two eigenvalues. It's going to give me lambda equals 0, or lambda equals 5 multiplicity 2. So the best case is when you get 3 eigenvalues for a 3 by 3 system, so that you can just plug them in and come up with 3 eigenvectors. When you get a multiplicity, sometimes you can find 2 combinations that will give you linearly independent eigenvectors. Sometimes you can't. So let's see what happens here. We're going to start with the lambda equals 0. Substitute it in, solve a minus 0 times I times k is equal to 0. That subtracts 0 across the diagonal. So we just have our original equation. K is going to be a 3 by 1 matrix. And 0, again, is a matrix consisting of all zeros, a column matrix. I could rewrite this as a system of equations and solve it. What I did is I I did row operations to solve the system. Notice that I took my second row, brought it up here to the first row, right there. Took the last row, put it up here at the second row, and then I had a row of all zeros because I ended up with two rows that were identical. Anyway, so I had a linear combination that I worked with to rewrite the system to get the equations to solve for k. I get k1 plus 2k3 is equal to 0, and 2k2 plus 5k3 is equal to 0. Both of these equations involve k3, so I solved for k1 and k2, and to avoid fractions I let k3 equal -2, so that -5 times -2 gives me 5 for k2, and -2 times -2 gives me 4 for k1. So again, you could have other answers there. And this is one solution, because my lambda is 0. This would be times e to the, oh gosh, that's horrible, 0t, which is just 1. So I get just x1 is the matrix, column matrix 4, 5, 9. Okay, so let's see what happens when lambda is equal to 5. When lambda equals 5, we want to solve a minus 5i times k equals 0. So here we're subtracting 5 across the diagonal. And we form a system that this system of coefficients can be reduced using row operations to 1, 0, 2, and 0, 1, 0, and 0, 0, 0 to tell us that k1 plus 2k3 equals 0, and k2 is equal to 0. So k2 is 0, and k1 is -2k3. So if I let k3 equal -1, then k1 is -2 times -1, which is 2. I get a second solution of the column matrix 2, 0, -1 times e to the 5t. But it only gives me one eigenvector. I'm not able to get two linearly independent eigenvectors. So we're going to construct a second solution by finding another vector p, where a minus 5i times p equals k, gives us this system, which in the first row it tells you that -4p2 is 2. Second row tells you p1 minus 5p2 plus 2p3 is 0. And the third row tells you that 2p2 is equal to -1, which is equivalent to that first equation. So knowing that -4p2 is 2, that tells us that p2 is -1/2. And if p2 is -1/2, then -5 times -1/2 is 5/2. And I can solve for p1 by bringing across the 5/2, it makes it negative. And by bringing the 2p to the third across the equal sign. And then I'm going to choose a value for p3. Choose 1. That'll give me negative 2, which is the same as negative 4 halves, plus negative 5 halves. Gives me P1 is negative 9 halves. Okay, so the second solution is of the form k times t e to the 5t plus p times e to the 5t. Notice that multiplication of t times the power of e is similar to what we saw in solving higher order differential equations with constant coefficients. That you just multiply by t and then t squared and so forth for multiplicities. But here we've got a combination of the e to the 5t and t e to the 5t, giving you one solution. So the t e to the 5t is multiplied by our vector k, which we had up here, and then plus p at negative 9 halves, negative 1 half 1 times e to the 5t. Gives us our third solution. And then our solution to the equation is c1 times x1 plus c2 times x2 plus c3 times x3.